This is LING 270, Language, Technology, and Society, Module 6, Artificial Intelligence. In this lesson, we'll be talking about the modern developments in artificial intelligence systems. So initially, the artificial intelligence systems I've shown you so far were very rudimentary, they could have very simple conversations and perform very simple tasks based on natural language instructions. But modern developments have shown a massive increase in the ability of machines. So we now have machines which have been developed which can play games and even beat human experts at them. For example, we see that there is the system called Deep Blue, which could master the game of chess. We see IBM's Watson being able to play the game of Jeopardy. And we also see Google's development of the AlphaGo system, which could play the Go board game. Now, the success of these various systems was due to three major advancements in artificial intelligence, one of which was the use of the technique called a game tree, which is essentially a way of performing a brute force task. We can see the importance of the development of neural networks to artificial intelligence, and key developments in natural language processing, which could give key advancements, particularly for Watson. So we'll start out talking about IBM's system, Deep Blue. So this was a program designed by IBM, and it to play the game of chess. And what Deep Blue would do is after each move in a chess game, Deep Blue would consider around 36 billion potential board positions or potential continuations of the game, and use these kind of possible future moves to determine what the best course of action is at any given state. Now, compare this kind of thing to humans. Humans are actually only capable of recognizing up to 50,000 future game moves. So this is just how much of an advancement the Deep Blue system is compared to a human. And the big claim to fame for Deep Blue is that in 1997, Deep Blue was actually able to defeat the chess grandmaster Garry Kasparov. So this was a very famous and highly publicized incident where a machine could actually defeat a human being at a particular task. So a key concept that was important for Deep Blue and is important for many other game playing systems is the use of what's called a game tree. So this is a way of structuring the possible moves that an artificial machine can use when deciding what move to make. So the way a game tree works is that you start with the initial state of a game. So in this diagram on the right here, we have an example of a tic-tac-toe game. So initially, the root of the tree, or the initial game state, is all empty. And then we represent each possible future move of the game. So each place where you could place an X as a branch off of that root. And then after each of these moves has been branched, further branches build off of that for the second move, so where the next O is placed. So each move in the each node in a game tree is a potential state of the game, and this is a way that you can structure the kind of the possible outcomes of a particular game. And you can see that since all of the possible moves are branched out at each node, we can see that the game tree grows exponentially the more moves you consider. So you see that we start with just 3 branches to start with in this example, but then we have around 11 in the next state, and then even more branches after that. And all of the possible moves of this game state continues to grow exponentially after that. So an artificial intelligence system can basically consider all of the possible states of the game by using a game tree like this. So looking finding out what happens if if every possible move was made. And whichever move leads to more success should be the next move that the artificial intelligence system should make. So that's kind of the idea about a game tree. And this was a technique that was fundamental in how Deep Blue functioned. Now, using just a game tree by itself kind of runs into a problem, which is called the scalability problem. So as I mentioned before, so AI systems and Deep Blue often use a brute force approach like this. In other words, they basically find the solution to a problem by trying out all possible solutions to it. Now, the thing is, some problems are not very amenable to this kind of solution. And this is because the number of possible solutions, it may be very, very large. So one example of a problem like this, which many computer science students will be very familiar with, is this idea of the traveling salesman problem. So the traveling salesman problem asks, what's the best way to make a single circuit path that visits each city with the smallest possible distance. Now, if you wanted to do this calculation by trying out all possible routes, you would have to try out n factorial possible paths. So if you're trying to find a route that goes through all the state capitals, as you see in the bottom right picture, for example, you would have to try an astronomical number of possible routes in order to find the best one using a brute force method. And so a game tree, like I talked about in the previous slide, runs into this kind of problem, because at each stage in the game, the game tree grows exponentially in terms of its number of branches. And it's not enough for many of these games just to try out every possible solution. So that means that you need to kind of try to think smarter rather than harder when we're developing an artificial intelligence system. But nonetheless, systems which can consider very many possible future states of a game are very powerful. And part of the reason that they're so powerful is due to the fact that there's been a trend where the computing power of a machine roughly doubles every 2 years or 18 months. And this kind of phenomenon was noticed a while ago, and it has been called Moore's law, which says that the power of a computing system expressed by the number of transistors, a basic kind of circuit within a computing chip, will double predictably over time. And so it's been this is a trend that is kind of held true for a very long period of time, but we are increasingly hitting a limit where we can rely on the increasing power of computers. We can't just rely on the ability of computers to use brute force to solve tasks. So yeah, we probably can expect there to be further advancements in computing technology, but there we will eventually run into limits. So we need to think of ways of being of making intelligent systems which make more efficient decisions, or make decisions which are more smart rather than hard. So a system which actually kind of embodies this kind of idea that works smarter rather than harder is the AlphaGo system. So AlphaGo was developed by the company DeepMind in 2017 to play the board game Go. So a Go board is shown on the bottom right here. This is a board game that's popular in East Asia. Go was initially thought of as a kind of game that could not be mastered by machines and could only be played well by humans. And this has to do with the fact that the game of Go has a high branching factor, which is to say that if we make a game tree of a Go game, like I did for tic-tac-toe earlier on, each node would have a very high number of branches. And that means that even just going a few moves into the future would make a very, very large number of possible game states in the future. So this makes a kind of brute force tree search very, very difficult to actually implement. So the developers of AlphaGo decided that what we need to do is make a system which can, instead of trying out all the possible moves, why don't we just try out the good moves and see what those moves will lead to. And in order to determine what a good move is, they had their artificial system, AlphaGo, play a lot of practice Go games, and then use a neural network to learn which moves tended to lead to winning outcomes. And eventually that kind of accumulated knowledge would eventually help it win Go games in the future. So here we can kind of see this idea of intelligence at play, the ability to learn from its environment and apply it to new situations. And ultimately, the developers of AlphaGo were successful. They were able to defeat the Go expert Ke Jie, who at the time was the highest ranked player of the Go game. So the developers of AlphaGo were actually able to make a computing system master the Go game, which previously had been considered impossible. So as I mentioned, a key component of the AlphaGo system was the use of a system called a neural network. And this is a technology which is very fundamental for artificial intelligence systems used today. So it's based off of the idea that we find in nature. So we see that in nature, our brains and neural systems of biological organisms are composed of a bunch of little neuron cells, which you can see in the top right here. These basic neurons are combined into a complex network that can actually kind of learn from its environment and change the strengths of its connections. And the neural network, an artificial neural network that used in artificial intelligence today, is intended to be a computational approximation of this kind of basic idea. So the strengths of the connections between these little cells are adjusted based on the kinds of inputs and outputs that it sees. So eventually this network kind of adjusts itself so that it can better model the relationship between its input and its output. And the idea behind neural networks is that with enough examples and with enough training time, these models will actually be able to mimic human behavior when, or be able to understand the relationship between the input layer and the output layer. I have a link here to a demo of a neural network where you can actually see how a trained neural network for identifying a handwritten digit actually causes these various connections between neurons to light up and kind of show how the network has learned these particular patterns. So this is an interesting idea of neural networks. So neural networks is particularly common in used in the field of NLP, and kind of going back to this idea of talking about the exponential growth or difficulty in the problems that AI has to tackle, using machines to deal with natural language will very frequently run into these kinds of problems. In particular, natural language sentences can be ambiguous and they can be parsed in many different ways. So for example, if we have a sentence like Kim and Sue or Lee and Anne, this kind of sentence can actually mean a lot of different things, and it depends on how we kind of group them together. For example, we can either consider that maybe we're talking about Kim and Sue together as a group, or Lee and Anne together as a group. That might be one potential meaning of this. It could also mean that we could also have the meaning Kim and Sue or Lee and Anne. So that means we have a group of 3 people, and the second person might be Sue or Lee. So how these kinds of units are grouped together is actually ambiguous, and there are many different possibilities. And the longer the sentence is, the more ambiguous it becomes. So we can see that there's this exponential vulnerability here as well. Additionally, natural language sentences can be virtually infinite in length. For example, we can make a sentence such as, John saw a boy and a girl with red wagon with one blue wheel and one white wheel dragging on the ground under a tree with the huge branches. So we can see that we can keep adding on phrases to further describe the situation that we're talking about. So it's necessary for an artificial intelligence system to be able to deal with this kind of scalability. Yeah, and we could add even further descriptive phrases to this if we would want to. And now searching through all the possible sentences that could be developed in English is not a feasible task. And that's why you need to think kind of smarter and harder. And neural networks are a very key factor into this kind of development. So one major development and a very kind of technique that we might consider to be very intelligent is this task of question answering, which has received a lot of attention from in natural language processing field. So systems have been developed which are actually able to answer questions to the degree that they can actually compete against humans in a trivia competition. You can see this, for example, in at the North American Association for Computational Linguistics in 2016. So this is one example of a quiz bot that uses Wikipedia as its knowledge base. And also there was a high profile example in 2011 where IBM developed an artificial intelligence system that could play the game of Jeopardy. Now, when we're talking about the field of question answering, there are two kinds of questions that can be asked. So one of which is a closed domain task where we answer a question that is related to a specific field. So the artificial intelligence system kind of already knows to limit its answers to a particular type. There are questions that are more open domain. So they are kind of general questions that require some world knowledge. And the game of Jeopardy is kind of a game that is more in this kind of field. So Watson, as I said, was a very famous public demonstration of an artificial intelligence system which could answer questions in this way. It was a cluster of 90 IBM Power 7 servers and 16 terabytes of RAM. So we can see it is a very, very powerful set of computing machinery. And it had a very large knowledge base, which consisted of many encyclopedias, dictionaries, thesauri, news wires, and literary works. On top of that, to encode a kind of word knowledge, Watson was also provided with a set of taxonomies and ontologies. In other words, what this kind of means is IBM was given a kind of diagram that says, for example, dogs, cats, fish, rabbits, etc. are all kinds of animals. Cars, bikes, trucks, boats are all kinds of vehicles. So these kinds of categories, taxonomies, and ontologies that we know about as world knowledge were provided to Watson so it could better use its world knowledge to answer these kinds of questions. So Watson would use this kind of world knowledge and its natural language processing system to parse the Jeopardy question and come up with an answer. And its top 3 answer candidates would be shown to the audience along with the competence scores that Watson had in it. And I have a demo that I've added in these lecture videos where you can see Watson in action. Now, so we can you can see from the demo that Watson is able to answer a lot of questions very accurately and very well. But nonetheless, there are a lot of limitations as to Watson can actually answer. So for example, Watson was asked, it was the anatomical oddity of US gymnast George Iser who won a gold medal on the parallel bars in 1904. Watson answered, what is leg? And the judges ruled that this was incorrect because the correct answer is that the anatomical oddity of George Iser was that he is missing a leg. So Watson kind of didn't really give as much information as the judges wanted, possibly because Watson had difficulty parsing the question. Another question was, its largest airport is named for a World War II hero, its second largest for a World War II battle. Watson answered, what is Toronto? And with a lot of question marks indicating that Watson had a lot of uncertainty as to this answer, where the correct answer is Chicago. So we can see that although Watson is able to answer a lot of questions, so we can see that Watson has a very sophisticated system that can parse a question, but it still falls short in a number of respects. So for example, Watson wasn't able to say that George Iser was missing a leg, and Watson also, when asked about a US city, gave a city in Canada. So that's kind of a very basic mistake and shows that Watson actually does need a lot more sophisticated technology to be improved. So there's a lot of room for improvement for Watson as well. But nonetheless, we can see Watson is a very powerful machine. Now, a lot of Watson's strengths owes to the fact, if I go to the previous slide here, that it's based off of a very large set of computing power and a very large set of databases and ontologies. So you might wonder if a machine simply has this huge amount of information, does that really mean that Watson is intelligent? Or is it simply just able to be so successful because it has this large set of information? So it's kind of ambiguous as to whether Watson can be really considered intelligent or not. And I invite you to kind of consider that question as well. So to conclude, AI systems of the modern day can actually outperform humans in a variety of very complex tasks and games. So we can see that AI systems can play games of chess and Go, and even a language game like a trivia game like Jeopardy. And we have seen that the ability of artificial intelligence systems to achieve this success are largely due to techniques of brute force, such as through game trees, but also there were critical developments in natural language processing which enabled Watson to play Jeopardy, and the use of neural networks, which allow an artificial intelligence system to learn from its experiences and produce better solutions in the future. But nonetheless, as we've seen, these systems are not perfect, and there are many more improvements which are still possible and which we can still make. So this would be an interesting thing to consider. And this is especially important because we can't rely on the increasing power of computers. We have to make artificial intelligence systems which need to work smarter and not harder.